last week, I briefly reviewed the topics covered in the control module, year 2 module. We discussed how to process a design for a control system. I discussed about overall control system, what type of the control system we have. We have automatic control system, manual control system, open loop control system, closed loop control systems. And I also briefly talked about the dynamic response, frequency response, and poles and zeros. Any question? Any questions?
No. That's good.
That everybody studied or didn't study? Okay. So what I will discuss today, it is the effect of the pole locations on the dynamic response. I will talk about the time domain specifications, and if I have time, I will talk about the effects of the zeros and additional poles. But I don't think we have enough time to talk about this part. So, we talked about the poles and zeros. What is the pole of a transfer function? What is the pole? Where is this now, guys? What is the pole of a transfer function? The root of denominator. And what's the zeros of the transfer function? Roots of numerator. And we discussed that both zeros and poles significantly affect the shape of the linear response of a linear system. Correct? But today I want to discuss how the location of poles, specifically poles, will affect the time response of a dynamic system, a linear dynamic system. If you look at the S-plane or complex plane, we have the imaginary axis, we have the real axis. And in the S-plane, we know that the S values are a complex numbers, combination of the real part and imaginary part. Is that true? Okay, good. For the simplest transfer function we have, what's the simplest transfer function we have? What's the simplest first order transfer function? We have just one pole on real axis, correct? We divide the plane to left-hand plane and right-hand plane, or left-hand side and right-hand side in terms of the stability. We discussed about it. So look, assume I have a pole on the in the real axis on the left-hand side. How the response will be? What shape of the response do we have? Exponential response, correct? The response will be something like this. Exponentially goes to 0 if we have the first order system, okay? But how the response will change if the pole relocate closer to the imaginary axis or relocated to far from imaginary axis? The shape would be the same, but the rate of decaying or going to 0 is slower if we have poles closer to imaginary axis. If we have far from imaginary axis, it quickly goes to 0. What parameter we define in terms of that? Time constant, if you remember for the first order system. Okay? So the location of poles for the first order system or simple roots on real axis just depends where it is, shows how fast it decays to 0. Okay? Another type of the poles can happen if we have a simple pole on imaginary axis instead of having the poles on real axis. In this case, we have a sinusoid output, okay? But what's going to happen if I move this pole closer to the real axis or far from real axis? What's going to happen? The shape will be sinusoid, but the only thing will change is the frequency of the response. We go up to from the real axis, we have higher frequency, so this is so faster. But here I have lower frequency, I have a slower response, or response with lower frequency. So if I have the simple pulse on the real axis, I have an exponential response. Depending where is the pole located or how much is close to the imaginary axis, the rate of decay will change. If I have a pole on imaginary axis, a single pole on imaginary axis, the output response will be in the shape of sinusoid. But depending where it is, the frequency of the response will change. Is that clear?
Yeah.
Okay, good. The other location for the pole is that we have a complex pole anywhere in these two areas, quadrant. In this case, we have a decaying sinusoid response. Okay? It starts with the sinusoid response, but it decays to 0. In fact, it's a combination of this one and this response. Okay? This is the combination of these two responses. Can you see the... Is that clear to everyone, the picture? Okay, good. The other case that can happen, we have a pole at origin. If we have, oh yeah, you have the lecture notes. Yeah, I forgot. If you have a pole on origin, depends what's the type of your system. If you have type 1 system, I will explain later about the type of the system. And your input is the step input, you will have a constant response. Okay? But again, this is still tricky. Depends on the type of the system. But assume that you have the type 1 system and you have the step input, the response will be constant. You don't have any decay or you don't have any oscillation. So another case is that I have a pole right-hand side on real axis. Again, first order system on real axis. In this case, the system is unstable because I have pole on real axis, on right-hand side of the plate. It goes to infinity. When time grows, it goes to infinity. But how about if I have a pole here? What's going to happen? Yeah. Still the system is unstable, but it goes to infinity much more faster. The shape is almost the same, but it quickly goes to infinity. If we have the higher is much far away from the imaginary axis, the rate of divergence is so fast. The last case is that I have a complex pole in the right-hand side of the plane, a complex conjugate. In this case, again, I have the oscillatory response, but the amplitude of the response starts increasing and goes to infinity or diverge. Okay? So this is the whole cases that can happen for a dynamic system. Doesn't matter. It is a spring damper mass system, or it is electrical system, it's a hydraulic system, whatever you have. If it is the first order system, we have poles on the real axis. If we have the second order system, we have the complex poles, right hand side or left hand side. Or in some cases, we have just poles on imaginary axis. Okay? So, we can categorize the poles or the response as the stable or unstable. We don't care about this one. We don't want our system response like this in any case. We just care about left-hand side of the plane. Okay? Clear? Any question? No? Good. So, now we know how the system will respond depending on where is located roughly the poles of the system. You studied very well the first order system in control year 2, and you know it's simple. We have just time constant, and the response will be in the exponential form. Here I would like to discuss about the second order systems. Second order systems are very common systems in reality, and most of the system can be modeled roughly as a second order system. For the second order system, a stable second order system, the poles are in this shape, are complex conjugate, minus sigma plus minus j omega d. This is the real part, omega d is the imaginary part. Correct? If I want to shape the denominator of the second order transfer function, I just need to multiply these two roots together. So the form will be s plus sigma s squared plus omega d s squared. Omega d is imaginary part, sigma is the real part. Correct? If I reshape this transfer function as its original one, the original transfer function has the form of h of s equal to omega n s squared plus 2 zeta omega n s plus omega n s squared. If you compare this denominator with this standard representation of the denominator, we can find that the sigma is equal to zeta omega n. The real part is zeta omega n, and omega d, or damping frequency, is omega n roots of 1 minus zeta squared. Okay? So both real and imaginary part are functional two characteristics of the second order system: damping ratio and natural frequency. So the location of poles all depends on the natural frequency and damping ratio of the system. If I have a second order system with zero damping ratio, it means the real part is 0. I have just imaginary part. What's going to happen? What's the type? What shape of the response do I have? Sinusoid response. Correct? Because I have poles on imaginary axis. If I put zeta equal to 1, damping ratio equal to 1, omega d will be 0, and I have just a real part equal to omega n. What type of the response do I have? First order. Exponential response. Exactly. So look, the location of the real part and imaginary part both depends on natural frequency of the system and damping ratio of the system. By playing or adjusting these two variables, we can control our system such that give us proper response or desirable dynamic response. Clear? Any question? Okay. We have a complex poles or complex numbers for the second order system as a root. We can show the roots as a real part or imaginary part, or we can show it as a polar system. If I show the imaginary, the complex poles as a assume I have two poles, two complex conjugate poles on the system, on the S-plane, okay? I can show it either by the real part and imaginary part. The real part is sigma, the imaginary part is omega d, correct? S1 is minus sigma plus j omega d, or minus sigma plus j omega d. So the imaginary part is plus minus omega d, and the real part is minus sigma. Is that clear? If I show this this pole as a polar system, I will have a radius of omega n. Why the radius is omega n? Why the radius is omega n? Okay. If I want to calculate the radius of this complex conjugate, amplitude or R is equal to roots of sigma squared plus omega d squared, isn't it? Is that clear? So what's the sigma squared is zeta omega n squared plus omega d is omega n roots of 1 minus zeta squared. If I add these two squares together, I will have omega n squared. So this one will be roots of omega n squared, which is equal to omega n. Okay? So the radius is omega n. I need to calculate this angle as well, because in the polar system I need to have a radius and angle. If I calculate the angle of this system, theta will be equal to sine inverse of zeta. Why? If you look at this theta, sine will be omega, sine inverse will be omega n. This side, which is zeta omega n, look, sine inverse theta is sine inverse of sigma over omega n. Sigma is, which is equal to sine inverse of zeta omega n over omega n, which is equal to sine inverse of zeta. Okay? Clear? So the angle will be sine inverse of zeta, and radius will be omega n. Look, using, yeah.
Can you write it bigger? Because
You can see here. I need to repeat it again. Yeah, okay. I think it's better to write by black. Look, A or R is roots of sigma squared plus omega d squared. Sigma is zeta omega n, and omega d is omega n roots of 1 minus zeta squared. If you add sigma squared plus omega d squared, here you have omega n. Okay? And theta is exactly the same as I have written there. Sine inverse of zeta omega n over omega n, which is equal to sine inverse of zeta. Okay? If you look at this triangle, you have this side, which is omega zeta omega n, and you have this side, which is omega n. So sine inverse will be zeta omega n over omega n. So tell me, what's going to happen if theta is 0? If theta is 0, what's the location of the poles? First, let me see. When do I have theta equal to 0? When zeta is 0. Damping ratio is 0. If damping ratio is 0, the poles come here. Okay? And this one comes to here. So I have two poles on imaginary axis. If theta is equal to 90 degrees, which means zeta is equal to 1, I have poles on real axis. If zeta is between 0 to 1, I have the angle between 0 to 90 degrees, and I have a complex conjugate pole. Correct? Do you remember what was the name of the system when the damping ratio was 1? Critical damped system. When damping ratio is greater than 1? Overdamped system, exactly. And when damping is between 0 to 1, is the underdamped system. When the damping ratio is 0, we have free body response or no damping system. So in this case, when theta is equal to 0, which means damping ratio is equal to 0, in this case, omega d is equal to omega n, and we have two complex conjugate poles on imaginary axis. If theta is between 0 to 90 degree, which means damping ratio is between 0 to 1, omega d is equal to omega n plus 1 minus theta squared, and we have underdamped system. We have two complex conjugate poles. When theta is 90 degree, it means damping ratio is equal to 1, and omega d is equal to 0. Okay? And we have two repeated real poles, or critical damped system. Is that clear to everyone? Any question? No? I see some smile on your face, but I don't know it's real. Okay. Anyway. And if damping ratio is bigger than 1, I have overdamped system, and they have two poles on the real axis, two separated poles. Okay, so now I know the effect of the location of poles on the system and how the location of poles will change when the damping ratio and natural frequency of the system will change. Correct? Now I want to justify my time response. I want to see, is my time response fine or not? How can I judge my time response? How can I judge the time response of a dynamic system, second order system? For example, you have a sinusoid, decaying sinusoid response. How can you define it as a good response or not?
Is it by the
I think your answer was correct. Yeah.
Is it part of the quadratic?
Pardon?
Is it the inside of the roots of a quadratic?
No.
That equals 0.
No. We need to define some specifications. Okay? We need to have some targets, and based on that target, say, okay, my response is good or bad. How we can define the specification for the second order system? We can define different specification. Assume I have this response, a step input response. Okay? What can I define for this response in order to evaluate or judge the response? Is it good or bad? I need to define some specification. One specification that I can define is the raising time. How much fast is the response? It quickly responds or is sluggish? The system is sluggish. So if I can't define the time rising time as time which the response reaches to 10% of its final value, and the time which reaches to 90% of its final value, which is here in for the unit step input, it's 1, I can evaluate the swift of the response or how fast is my system. Okay? Another specification is the peak time or maximum overshoot. When the system reaches to its maximum value, or how much overshoot I have with respect to the final value of the system. Okay? Another specification is that when my system is settling down, okay, or when the system approaches to its steady state conditions. Okay? So, in fact, settling time. Tell me, if you have the aircraft, which parameters are most important for you?
No overshoot?
No, aircraft, military aircraft.
Oh, I see.
If you have military aircraft.
Rise time?
Rise time, exactly. It should be so fast. We don't care how much overshoot this system or military aircraft has, because the comfort is not at all important. Okay? The speed of the response is important. The settling time is not important. Just what we need to have a very fast system. But if you have the passenger aircraft, which one is important for you? Maximum overshoot and settling time. Okay? Because if you have a huge overshoot, the airline couldn't sell any more tickets. Okay? So, or in terms of the mechanical system, other mechanical system, assume you have the material you want to control it, or you have the actuator you want to control an actuator. If you have a huge overshoot, you will damage the whole actuator, because the huge force will act on the actuator, or huge voltage will act on this actuator, and you will burn the actuator. Okay? So the amount of the voltage comes to that one, you can't say, okay, I don't mind 100 overshoot for the voltage input. So depends what are you looking for. You have different specification. But at least you have some variables to judge your system. So in summary, we have the rise time, TR, which is the time it takes the system to reach the vicinity of its new set point. The set point is the steady state response. The settling time, TS, which is the time it takes the system transient to decay. We have overshoot, you know what's that one, and the peak time is the time that the system reached to the maximum value. So we have this TR, TS, NP, but how we can calculate? When you want to design a control system, you can't plot by hand, or you can use the MATLAB to calculate this one. You need to have some feeling, some quick tools to design your control system, correct? So we need to look for a formula for each of these variables for a general second order system, for any values of the damping ratio or natural frequency. Correct? Any question? Am I fast in teaching? I am? If I am, tell me. I will go slower. I received one email from your friends last week that in last lecture I talked so fast. So this week I'm trying to be slower, but answer that I need to give you some information in a limited time. So it's both sides. You need to read. I post most of the lecture notes before the class time. So if you go through it and study, that will be perfect. If you read your lecture notes for the last lecture as well, will help you to understand these new materials better. But okay, how can I calculate rise time? Rise time depends on the pole location, and it is a function of the damping, as I said. The response of the second order system is just function of the damping ratio and natural frequency. Correct? So I need to see how these two parameters affect the rising time. If we have the second order system, under damped second order system, when you change the natural frequency and damping ratio, the settling time, the rising time follows a simple equation. If we assume we have the zeta equal to 0.5 as average of the damping ratio of the system, TR is almost 1.8 over omega n. It is independent of So it doesn't matter how much is your damping ratio, your raising time won't change. If you want to change the raising time of the system, you need to change the natural frequency of the system. Okay? Is that clear? Again, keep in your mind, the equations, the formula I will give you for the raising time, for the maximum overshoot, and or for settling time, are just for the standard second order system, omega n squared over S2 plus 2 zeta omega n S plus omega n squared. But in reality, the systems are much more complicated than this second order system. This is just as a guideline for the design. They are not accurate. How the complication of the transfer function will affect the standard response, I will discuss maybe next week. But keep in your mind, the equations I give you now is just for the standard second order system. Okay? So, how can I define the maximum overshoot? Maximum overshoot can be calculated mathematically if I have a second order system or second order transfer function and it is subject to a step input, the response yt will be in this form. In practice at home you can calculate this one because you just need to use the Laplace inverse transform and the Laplace inverse table. But trust me and believe me, this is the correct response. Okay? If I have the response as this one, and I want to calculate the maximum overshoot or peak time, how can I do that? Differentiate and equal to 0. If you want to calculate the maximum or minimum of a function, you need to take the derivative of this function with that time if you are maximizing against the time and put it equal to 0. Okay? So I do the same here. I have yt. If before going to that way, I need to reshape this transfer function, this time response, to make it a little easier. If I use the trigonometric identity, which says that a sine alpha plus b cosine alpha is equal to c cosine alpha minus beta, c will be root of a squared plus b squared, and beta is tangent inverse of a over b. If I apply this formula to this response, I can reshape yt as this one. Okay? I know it is boring. The only way that you can make it more fun, ask questions. Okay? I don't have any other ways or choices to help you. Okay. So if I get the derivative of this function, time function, I will get to this formula if I put it equal to 0, in which case always this one is 0. When y dot t is always 0, if omega dt is 0. Okay? So, if I put omega dt equal to 0, the peak time will be equal to pi, or which means the omega dt is equal to pi. So Tp is equal to pi over omega d. Correct? Any question? Yeah?
Do we have to know how you derive that, or?
No. Maybe I ask you to. No, I won't ask you, okay. And a better news, I will give you this relation if you need an exam. But you need to know how to get to this formula, okay? So to calculate the maximum overshoot, I just need to substitute Tp in T And if I do that, I will get the maximum overshoot equal to exponential of minus sigma pi over omega d. Sigma is zeta omega n, and omega d is omega n roots 1 minus zeta square. So MP, if you put it equal to 0 and solve these equations, MP will be equal to E minus pi zeta over roots 1 minus zeta square for the zeta bigger than 0 and less than 1. If you look at this relationship, maximum overshoot is just function of damping ratio. Okay? So, doesn't matter how much is the natural frequency of the system. It won't affect on the maximum overshoot of the system. If I want to increase or decrease the maximum overshoot, I need to play with the damping ratio of the system. Okay? And here is the change of maximum overshoot subject to the damping ratio. As you see, if the damping ratio is 0, I have 100% overshoot. By increasing the damping ratio, the maximum overshoot will decrease. The most desirable damping ratio for the system is between 16% to 5% for a mechanical system. Okay? So, the last parameter is the settling time. We have different definition for the settling time. It's not a standard one. Sometimes it calls when the response reaches to 1%, sometimes 2%, sometimes 5%. But in this module, I will focus on 1%. If I assume the settling time is the time at which the response settles within 1% of its steady state value, I have again yt for the second order system equal to 1 minus this complicated relation. And since our steady state response for steady state value is 1, I put 1 here as a yts. Then I need to solve this equation for t. If I solve with this equation for t, I will get the zeta omega n ts equal to 4.6. Or ts is equal to 4.6 over zeta omega n. If you look at here, settling time is function of both damping ratio and the natural frequency of the system. Okay? So, let's recap. I have second order system, a standard second order system. The poles are equal to minus zeta omega n plus minus j omega n root 1 minus zeta square. Now, I know if I have TR or raising time equal to 1.8 over omega n, the whole poles which its radius is omega n have the same raising time. Doesn't matter if your pole is here or here, here or here or here. The raising time will be the same for these all poles. If you choose another omega n, you have the semicircle, which all poles will have the same settling time, raising time. Sorry. And MP is function of just damping ratio. So, if I have poles in this line or in this line, all system will have the same overshoot. Doesn't matter, I choose poles here, 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 or on origin. Because all have the same angle, or they have the same damping ratio. For the settling time, again, all poles located on this line, a straight line, will have the same settling time. Okay? Getting more interesting and interesting. Yeah? So any question? Yeah.
For that last one, it's in between those two lines, right? They'll have
No,
the
no,
same-
just on line. Just on the line. Minus the omega n is the real part. They have to have the same real parts. And you? This one is overshoot, maximum overshoot, the middle one. Yeah. Okay, so let's summarize again. Yeah?
Sorry, so was it the first one, if it's in that radius, it all has the same rise time?
The same right time,
The
exactly.
second one is...
The same overshoot. Yeah.
So with the third, what was the third, sorry?
The third one is the settling time.
And is that,
When reached to the 1% of its final value, or a steady state value. Okay. So, again, to summarize, in terms of the TR, NP, and TS, you need to keep in your mind the formula, this relation we obtained are just for this transfer function. For the complicated system, which is the case in reality, we can use these relations as a baseline for our design. If we have higher order differential transfer function, or we have the zeros or poles on our system, how it will affect or change the response of the second order system, we will discuss it next week. So, assume we have a system, second order system. We want to see if we want to have the rising time less than 0.6 second, the maximum overshoot less than 10%, and settling time less than 3 seconds, which poles I can select from the left-hand side to give me these specifications or these targets. If I calculate TR, which should be almost 1.8 over omega n of my poles should be bigger than 3. I can do that. If NP less than 0.1 or 10%, it means damping ratio should be bigger than 0.6. And settling time less than 2, it means that zeta omega n should be bigger than 1.5 seconds. What does it mean? If you look at the S-plane, complex concave plane, this is the real axis, this is imaginary axis. From our relation, I know that if I choose the omega n in this radius, the radius of 3 or higher, I will have the racing time less than 0.7. Okay? But I can guarantee the other specifications. If I want to meet the maximum overshoot, I need to calculate the angle. The angle or damping ratio should be 0.6. For the whole poles behind these two lines, the damping ratio will be bigger than 0.6. Okay? For the raising time, for the whole poles that the real part are after this blue line, I will have the setting time less than 3 seconds. Because I want to meet all these specifications, I need to look at the common areas for these 3 regions. The common area will be the poles located in the shaded area won't give you these specifications. But the poles located after or behind this shaded area give you these specifications. Doesn't matter where you choose them. They need to be out of this shaded area. Let's give you example. Yep.
For the maximum overshoot, you got zeta is equal to greater than or equal to 6.
Yeah.
How should you make the line for that?
If you calculate the theta, theta is sine inverse of zeta.
Yeah, all right.
Okay? You can calculate the angle. Let's choose three cases. For my first design, I choose these two ports, two complex conjugate ports. Okay? If I choose this port, S1 and 2 minus 3.2 plus minus 0.3, the transfer function will be in this port. And the damping ratio will be 0.99 and omega n will be 3.2. Another case, I choose them further from the imaginary axis, was close to the damping ratio. In this case, I have this transfer function with damping ratio of 0.7 and omega n 5.66. And another one, two other ports much further from imaginary axis, but exactly on damping line. So if I have plot the response, you tell me which one is for the first system? Blue one, because we have higher damping ratio. The green one is for the second system, and the red one is for the third system. And if you look at this calculated raising time, maximum overshoot, and settling time, you see we meet the maximum overshoot and settling time for the all cases, but for the, I think for the TR, for the first system is not, it hasn't met. Why? Because we have chosen, look, if you look at the first system, is very close to our region, okay? And the relation we had are approximate relation. They are not accurate relation. So you need to consider safety factor a little behind that, those region. We don't have time. Let me see what's the next. Okay. Quickly, as a summary of all system, if you want to design a system, if your raise time is not fast enough, you can improve raising time by changing the natural frequency of the system, increasing the natural frequency of the system. If this overshoot is too much, you need to increase the damping ratio. If the transient response is too light, you need to play with zeta omega n. As you see here, I have 3 zeta and different omega n for the whole 3 systems. Please listen up. For the 3 systems, I just changed the omega n. If you look at, for the 3 of them, the maximum overshoot is the same. The only thing is changing is the rapidness of the system or response. Okay? Or in another case, I fixed the omega n, I just changed the damping ratio. As you see, the overshoot will change. So have a look. One thing, in order for you to practice at home and see how these systems will change, I developed for you I have posted on Storyland. Please have a look, but I can't find it here. Okay, it's here. Okay, guys. What happened? Okay, guys. Look, please listen up. I have posted the code for this simulation. Please look, you can change 3 parameters, stiffness, damping, and mass of the system. And see how the response will change when you change these characteristics. For example, if I increase the damping ratio of the system and I leave it, I will have the overdamped system. Okay? If I increase the omega n and clear graph and run it, look, for the same damping ratio, you have faster response. You have the code on Storyland. These 2 codes, download both of them, and try to play with these parameters and see how the response of the system will change when the omega n or natural frequency or damping ratio of the system will change. Okay? So see you next week, and sorry, see you Thursday. Please, if you have any feedback, send to me. I'm trying to slow down a little more, but this is the slowest I can go.